In this video segment, I'm going to be repeating the problem that was done in video 25. The difference is that here the pressure is not going to be constant. It's going to be, it is constant, but it's not slowly applied. Instead, it is suddenly applied, and therefore the problem becomes a dynamic problem. So we're not dealing with a static problem anymore. It's dynamic, and the boundaries of this plate also, as opposed to the previous video segment, are simply supported. So let me move on to the slide presentation. The problem that we're going to look at is shown here. Uh, a square plate simply supported at all four edges, and the rosette is shown down below so that we can see that they're aligned. This rosette is aligned with the global coordinate system. Now, the other thing is that I'm going to do this problem with two plies only, and the plies are 0 and 90 degrees as shown here, and they're symmetrically placed about the reference surface. Therefore, this is not a symmetric stacking sequence. However, the reference plane is exactly halfway between the top and the bottom. Now, why I took this particular problem is that because in Reddy's book, this problem is presented and solved in its entirety, and there are some results there that I want to compare it against. Now, the thickness of these two plates, when you look at the overall geometry, actually, this is 25 centimeter, 25 centimeter, and the thickness of total thickness of the laminate is 5 centimeter. Now, this is really not a good set of numbers that they have picked, because generally speaking, the thicknesses must be smaller compared to a dimension. But as far as comparison is concerned, because he's solving it partly analytically, it really doesn't matter. So we're gonna pretend that the classical laminate theory that is used, or variation of it that's used in the software CATIA, is applicable. Okay, in spite of the fact that this is a relatively thick laminate compared to the overall dimension. Now, because of the nature of the problem, nature of the stacking and the angles, orientation, there's a two planes of symmetry. In other words, I don't have to model the whole thing. All I need to do is to model a quarter of that, but I'm not going to ignore that. I'm going to ignore that and model the entire geometry. The properties are given. These are taken from Reddy's book, and there's a misprint somewhere in Reddy's book. This number, uh, somewhere in the book, it says it's 8 kilogram per meter cube, or something along that line. So this is the correct dimension. And the load is, notice that the load here is uh, uh, 100,000 Pascal, or almost zero point 0.1 megapascal, and it's applied impulsively. In other words, it's not that I apply the pressure starting from 0 and build it up to that number. It's suddenly applied, as if I don't know, a gauge maybe, or a valve is suddenly open, so it starts to vibrate. Well, we're going to come back. I noticed that I do need the density here, because dynamic effects are present. Now, I'm also going to be doing in a very rather unusual discretization. Only 4 quadratic elements is covering this geometry. I'm going to be doing it with only 4 elements, and the reason I initially did that was because the results in Reddy's book is actually a mesh like that. Okay, when he presents his finite element results, it is using a mesh of this type, and yeah, but that this is fine. So we have four elements, parabolic in nature. Now, so the way the strategy works is that you create a geometry and you create a plies. Okay, we already know that, and then you perform a static analysis. Now, in doing that, you need the restraint and the load. Okay, no problem there. And we have video 25 was precisely this problem. And then I'm going to extract, load is going to be set aside within that run, and the frequency, natural frequencies of vibration, natural frequency of the plate is extracted, okay? And of course, in order to, as I said, in order to find a natural frequency, you don't need a load, you need a restraint, so it uses those restraints, simply support at all four edges. Now, then we exert a transient dynamic module or yeah, transient dynamic calculation. And transient dynamics in CATIA is using the concept of modal superposition. In other words, it actually needs the frequencies that you just calculated, and of course it needs the restraints. Sure, it's going to inherit the restraints because of the using those frequencies. Obviously, it came from those restraints, and then uses the load and excitation. Load, using the load means that you apply in static one, you apply certain pressure, let's say, I don't know, 100,000 Pascal, and then the fact that it's applied suddenly means that we have to create an excitation and run it. Okay, and the concept of modal superposition is used. So CATIA's native FEA solver really cannot handle nonlinear dynamic problems. It's based on modal superposition and therefore linear dynamic analysis. Now, this is the graph that's presented in Reddy's book. There's a misprint here. This was not correct. Okay, and the shape that over a 400 microsecond, you're going to get two lumps here, so vibrating basically up and down twice. Okay, but I'm not going to use that because I don't know that there may be some other mistakes here. So instead, what I did, I ran it. These are the CATIA results. Okay, this one is for parabolic element. This one is for linear element, and then ran the same thing in abacus, and you see that they match pretty closely. Uh, Even these agree with Reddy's result, but you have to non-dimensionalize it. The presentation is different. Not that there are really, aside from that typo in the density, what is presented in Reddy may be okay. It's just that the uh, he has non-dimensionalized it. So you can see that these two, as far as the scale is concerned, they match. Okay, that's fine. All right, so let's go ahead and do the problem. Obviously, I need this thing in front of me because these material properties will have to input. So let's go to CATIA, first create the data for the problem that we're doing. So start, infrastructure, and material library. Double click on this. I'll call it transient problem, transient. Apply. Okay, so composite. Okay, the thickness, acute thickness was 5 centimeters. That's too big, right? 5 centimeter. Oh, there's two layers, so it's going to be 2.5 centimeters, right? 2.5 centimeter. The total laminate thickness was 5, so each laminate is 2.5 centimeter. Unidirectional, okay? And for analysis, I'm going to do 2D orthotropic, and we put in those numbers that we had. Now, let me read those off my notes. So E1 is, let me type here, 5.25, 5.25 e to the 11. Okay, so that's fine. Then E2 is 2.1, 2.1 e to the 10, 2.1, okay, 2.1 e to the 10, okay. Poisson ratio was 0.25, 0.25. shear modulus in the xy, which is 1, 2, is 1.05 e to the 10. In the xz, which is 1, 3, is same number as above, 1.05 e to the 10. Okay. And in the 2, 3 plane is 4.2 e to the 9. Yep. Now the density is 800 kilogram per cubic meter. Okay. So that takes care of this. Apply. Okay. Save this thing. I created a folder called Transient something. Transient, yeah, right there. And I call this thing dynamic or transient. Okay, I call it transient. You can give it any name that you want. All I'm doing is putting these things so that eventually, at some point, if I look at these material libraries, at least I recognize them. Okay, good. This is all done. We close it. Now we're going to go create a hot file. I'm going to call it transient. Okay. Go to generative shape design. On the XY plane, I will sketch a rectangle. Let's give it some dimensions. So this one is 25 centimeter. Move it here. 25 centimeters. And this one is also 25 centimeters. Exit. Okay. I'm not using planes of symmetry, so it's 25 or 25, the actual dimension of the plate. So we fill this thing, FILL, and join it. And make sure that the direction of the join is downward. Okay. This is to make sure that all the shell elements that are going to cover the surface has an upward normal, opposite to the direction of the joint. And let's create an axis system here, which is going to be used as my rosette. So let's move it off to the left a little bit. So minus 20 centimeters. You see, it's not going to be right there. Actually, this is too much. Minus 10. Make it minus 10 centimeter. Okay, so it's going to sit there, and we say okay, and let's make sure this is not checked. So the coordinate system, global coordinate system is checked. Okay, good. So save this thing, file, save management, save as, that folder, transient folder. Yep, very good. Okay, so now we're going to go to our composite design. First, create our composite parameters. So add a material. Remember, I created the database in that folder. Desktop, transient. They're right there. Remember this database I created? Say all right. Okay, so there we are. So the direction, obviously 0 and 90 are the standard ones I don't have to take. For rosette, you're going to add a rosette, and this is the rosette that I created, and we say okay. And we close this thing. We're done with this. So I'm going to hide the rosette. Hide it. Oops. Hide the rosette. There. Okay, so we're going to go to, well, let me save this first of all. And then I'm going to go to the advanced machine tools. We're going to our first attempt is going to be doing static analysis. Okay, although the problem is dynamic, I understand that. So this is a surface measure. You select this thing, and since I want only 2 elements in each direction, I'm going to make this thing. How about, remember this whole length was 25 centimeter. So I'm going to make it 12.5 centimeter. Okay, and parabolic, and mesh it. Notice that it gave me what I wanted, and exit. So immediately we're going to save the analysis file, save management. Here is the analysis. I'm going to put it in that folder, and I'm going to call it Transient, so that if I do something else, at least I recognize the name. Okay. Oops. Okay, that is Transient. Okay, we're done here. So we're going to go to generative structure analysis. The usual thing is, you know what? I forgot to create my plies. I'm really sorry. So let's go back here. We can go back. Completely forgot to create my plies. Let's go back to composite design right there. We're about composite design. So we're going to create our ply group. Things like this happen. Okay, so ply group. Remember, I jumped the gun too early. I went to the finite element analysis. I meshed this thing, whereas I had no plies here. Okay, so I went back to the composite design, as you can see here. You create a ply group, and the surface is right there. The draping direction, I always like it up. All right, so I have a ply group. I'm going to create 2 plies. Here's manual ply right there. See this? Select the ply group. And for the boundary, I select that sketch right there. For the attribute, the first one is going to be 0, okay? And the material we already picked, it's already picked. And then the 90-degree one, so where's the other one? Another ply in the same group. The boundary is still that same edge, okay? And the attribute is 90 degrees for the orientation. And we can always check this thing. So here's the ply exploder right there. And apply group, apply. Now notice that the reason it doesn't show is that because it is, you see, why did it not show? Okay, so something is hidden probably, so let me see for a second. In there. Did I create my plies? Plies are created, yes, yes. Let's see. Well, the plies are created and they have the proper angle. The first one is 0 degrees, you can see, and the second one is 90 degrees. There's a 90 degrees, but they're not showing, so why would that be? Let's see now. Analysis. Oh, you know what? It is showing. It's up there. Ooh, wait a minute. Where is it? Did I hide anything? Hide and show. Hide and show. Let's try it one more time. That's this. This is the ply group, right? Ply exploder. You select this, and let me change this thing a little bit. Let me put some other number. Maybe let's make it 200. Oh, whoa! It was way up there. Oh my God! So let's make this thing 5. It was up there, or 4, right there. Here. So this thing obviously it. Remember, each one of these was 2.5 centimeters. So if you make it too big, it's going to space them out and you can't see it. Look, if you make this thing 100 or 50, let's try it. Apply, it goes off the screen. It's up there, right there. So put it back. It was okay. It was okay. Let me cancel that. So we wasted some time here, but it was unnecessary. Okay, good. So now we're going to go. Now we're going to go back to our analysis. Okay, so let's go back to our analysis, generative structure analysis, right there. Okay, you can look at the mesh once again. Right-click mesh visualization. It's right there. Deactivate this. Okay, so why don't we import the properties? Okay, so where is this 2D property? Right there. Import composite property right there. The surface is right there. The support is right there, and we're doing it by plies. So let's go and select that ply group, and it's going to be symmetrically placed above and below that reference surface. Very good. I'm going to minimize these things. We don't need it anymore. All right. Okay. Yep. So let us hide the stacking engineering sequence and stacking sequence here. Let's hide the plies. And I'm going to hide my sketch. Remember that sketch? Because if I try to put some kind of restraint here because of the presence of the sketch, it won't take the edge. So hide this. Okay. Hide it. Hide it. There. Now I can select these sketches, these edges one by one. Okay, so let's apply our pressure. Remember, we are in a static case right now. We are in a static case. Okay, so restraints. Let's do this thing. This edge and that edge, they do not move in the direction Y. Okay, simply supporting that they don't move in direction Y, and up and down, of course. And these two other edges, these other two edges, they do not move in the direction X. They do not move in direction X and Z. That's what the simple support is. Now we're going to apply a pressure here. We're going to apply pressure right there. And the value was 100,000, right? So it was 100,000. I will put it, it really doesn't matter, but I'll put it down. And the reason is that if I put it as a negative, okay, I'm sorry, what I meant was I'm going to make it negative. The reason is that I want to reproduce graphs which look like this going up, okay? Otherwise, if you do it with a positive value, it shows you that it's going down. It's the same vibration except that displayed differently. So there we are, okay? Now, have I done, this is for the static problem. I think we have done everything. So let's save our analysis file, save management. There's the analysis. We already did that. Okay, so cancel. All we have to do is to say save. And we're going to run. Nothing exciting is going to happen. This is just going to bulge up like the previous video clip. Let's run it. Static load is going to bulge up. Okay, so there we are. Let me change the scale here. Oh, oh yeah, right there. See that? This is gigantic deflection. So let's do the following. Let's actually do this. I'm going to double click on this and average ISO. There we are. Horrible. I mean, obviously this doesn't make sense as far as we can always change the manually change the scale here ourselves. This is just for visualization purposes. Okay. Now remember, think about it. This is a composite plane, 5 inches thick. Okay. and made of carbon epoxy, and you put 100,000 Pascal on it. That's a huge load that you put in there. Okay, and it's gonna these numbers. Yeah, so okay, so that's okay. So let's leave this thing the way it is. Deactivate that. All right, everything was okay. Now, we want to extract the natural frequencies of this thing. So obviously we have to go and say insert a frequency case right there. Insert a frequency case right there. Insert a frequency case. And it says, okay, for frequency, don't give me load, just give me a restraint. So what we're going to say is that, okay, restraint, we're going to use, we click on the reference radio button here, and then go and select the restraint that you put for the static load right there, this. So what it does, it takes this restraint, which was simply supported on our edge, and use it for frequency calculation. Loads are totally irrelevant. Notice there's nothing about loads here. Okay, good. So let's go ahead and run it. It's going to run the static analysis again because I said all, which is unnecessary, and it's going to find the frequencies also. Okay, so let's see now. Here is the stuff for frequencies. Let's look at the deflection for the frequencies. Click. And hey, look, this is confusing, but that's because the scale is so big. Okay, so let me go here and show you what happened. First of all, double click on it, select average ISO, so that we get something like that. And these are the different modes of vibration, free vibration. So we say okay, and change the scale if it's bothering you. Now, you know, if I had used a fine mesh, things like this would not. But there's only four elements here. This is the first mode of vibration, and double click on it. And if you select the occurrence, it gives you all the extracted frequencies. Okay, and then if you go to the next mode, it's going to look like this, and the next one is going to look like that, etc. It extracts 10 modes by default. Okay. Now, please, if you have issues with the frequency of vibration, look at video. I think that's video 24. Yeah, I think 24 was vibrations. Okay. So these numbers are meaningless, of course, but the frequencies are not. The frequencies are okay. So all right. So we first did the static analysis. You will see that I need that later on, and I did a frequency analysis, so using the restraints that were already created in the static case. Okay, so save everything first of all. All right, now we're going to do a insert transient dynamics, transient dynamic response. You click on it, it says, okay, if you're going to do transient dynamics, first of all, you must have extracted the frequencies. You say, fine, we did. So you select it. So you go and check you go and find uh, right here, the frequency case. This was the frequency case that was used, that we just created. So use these frequencies, and then the load, it says, uh, if you already have something, go pick it. Otherwise, see, it says create the excite. Do you want a new excitation or a reference? So we're going to say new. Okay, fine. We'll see. We'll see what it means. So what happens in transient dynamics? Frequency was picked. Those are the things that we calculated. Now, for the load, see this is load excitation. You double click on it. Look at what it's asking. It says, okay, first of all, you have to give me a load. And the load was already created here. It was this pressure, right? Under pressure, selected load under pressure, right there. I can select that. But then it asks you also for, the modulation. Or this is the first time you're seeing it if you're only watching the composite video series. But I have done these things in the general FEA. So let me show you how. I don't have it. So can I create it? It won't let me create it. So I better go and create it first and come back and do it. So cancel that. We're going to come back. So notice that here there is a toolbar right there. You see this? This is the modulation. This is called the modulation toolbar right there. In our case, this pressure is applied constant immediately or instantaneously. So that's all I need. It's called white noise. Otherwise, if that pressure was varying with time, over time it was applied, then you can create your own Excel file and use that as the modulation right here, this one, modulation, time modulation. But in my case, it's instantaneous. You click on it. You don't have to do anything. You can call this thing a name that you want. But anyway, it creates the modulation for me. And if you look at it, it's right there. See this? It's under the finite element model. One of the branches now it says modulation, the white noise. So now let's go back and repeat this thing. Double click on the load excitation. For the load, select that pressure. And for the modulation, select that white noise that you created. Okay. Now, if you are happy with that magnitude of 100,000 that we applied as pressure, just don't worry about it. Use factor 1. But if you want to double that or whatever, then you can use load factor here, which is good. All right. That's it. Notice what happened is that, let me remind you what we did here. We did a static analysis because we needed the load there. We did a frequency because we needed the different frequencies. And finally, in transient dynamics, we use these frequencies and load and excitation. So that's what happened. Okay. All right. So this is it. Run. All. Now all means that do the static one and do the frequency one and do the transient dynamics one. Just to be on the safe side, you're going to say all so that you don't miss anything, and it's done. The reason it's so fast is because it's doing modal superposition. It doesn't integrate in time. One thing I forgot to do is the duration. See that over here? Over here, when I said transient dynamics, something that I forgot to do, I'm going to double click on it. We can look at it, but this is so what this is going to do is going to do it over a 10-second interval. I don't want to do that. So I want to go from 0, that's something that I forgot to do, now we're going to fix it, to a total time of 400 microsecond. So 400 e to the minus 6. So start at time 0, everything is at rest, no velocity, no position, no displacement, and then go all the way to that and do it in so many steps. The more steps you have in more, if you put too few steps, then the results are okay. So it's going to be jagged. The graphs are going to be jagged. So when I say graphs, I mean these type of graphs are going to be kind of choppy. So what I'm going to do here is I'm going to say, okay, I don't know, 80 or 800, and now run it. All. It's going to be very fast. Okay, good. All right, so what does that mean? Let's plot. Let us plot. This one we don't want it, so I'm going to deactivate it. Okay, so let us plot the deflection, displacement. Okay. Now don't let it scare you. If you double click on the translation here, notice that it allows you under the occurrence tab, it allows you to pick different times, okay? So obviously this is the initial time, nothing exciting happened. If you go 5 microsecond, very little deflection, okay? Very little deflection, okay? It's right there. Let me change the rendering here so you can see it better, right there, occurrence. And then you can select different times and it shows you the deformed shape. Now remember, the deformed shape, you have to scale it up or down if you want to see it, but these are initial times, so nothing exciting happened. Okay, so you go down, okay, and of course let me change the scale here, say default, there. Okay, so we say fine, go back here, double click, a different time. Initially, of course, everything is 0, then gradually as time builds up, this uh, this bulges out, okay? Okay, good, fine. So we can look at different times this way and find out what the shape is and deflections are. Now, these are not all realistic numbers because, I mean, so these are very tiny meters. Yeah, so very small. Okay, now what we can do is this. If you want to get a plot of, for example, variation versus time of a specific node. So, for example, some node, this middle node, there's a few things you have to do. Okay. So what you do is, by the way, before I do that for you, let me show you, if you want to get the stresses at a particular time, what you do. So you put the cursor here, generate image, stress, stress, okay, uh, stress, where is that? Full tensor stress, okay. If you double click on it, it allows you to pick under more, it allows you to pick the stress in different layers. There's only two layers here at different times. So this was C11, C22, sigma x, sigma y, tau xy, etc. So this is how you get to see the stress distribution in the laminates at different times. Okay, obviously initially initially 0, and they're very small, etc. Pascal, this is pretty much nothing. Okay, so I showed you how to see the stressor. But anyway, deactivate about this thing in the general FEA videos that I have, but and there are some that you can go and look at it, but I'll show you again. Okay, right here. So you put the cursor on this line, transient dynamic, right click. You see that? Generate a 2D display. See that? Generate a 2D display. You click on it, and then you say, okay, I'm not going to do this thing in a very fancy way. You just say finish. What it says is, okay, you go pick a node or a bunch of nodes, okay, and then show me what is it that you want to plot. For me, I want to plot Z only, displacement in Z direction. So I check that. It says go pick a bunch of nodes. So what I do, I minimize this, and I go and select this node. See that it lets me go and select different nodes here. This is the middle node that I want to select. You notice that it picked it up, and I say okay, add it, and okay. So it did create down here, either in the tree, or you can see down here, it's actually also down there, it did create some kind of a graph for me. So if you maximize that, there we are. Okay, now the only thing is that this is the amplitude. Okay, we want to see actual location, as opposed to always this is always positive amplitude. So you put the cursor there, right click, and say under limit, under not limits, format, you say real. Notice that it shows you the actual deflection. Okay, now the other thing is that this shows that you in meter. You put the cursor in the in the white area, right click, you say option, and this is the show it to in meters. So I'm going to say that use the limits that I described. I don't remember what limits I said, but let's see now. Uh, okay, I think what I did, my displacements or my length was in meters. So let me go fix this thing. You go to tools, options, and for length, let me use centimeters, and say okay. And now right click, options, use the selected options. So apply. Notice that now it shows it to you in millimeters. Okay, so this is what we've got, and this is in millimeters. This is in millimeters. The only thing is that it does not match what I showed you earlier, or maybe it does match. I'm not sure. Let me see for a second. Let me see. Oh, centimeters, okay. So we have a bunch of zeros, extra zeros there. So let's see now, 3 zeros, 5, 9. Here I have, uh, yeah. So there's an extra 10 there that is unaccounted for. Now I'm trying to see what is it that I might have made a mistake. I might have done wrong here. So let me minimize this. Let me check everything that we needed. First of all, my load, make sure that it is 100,000. Right there. You see that? The load here was supposed to be 100,000. Accidentally, I put 10,000 here, so I put an extra zero. They'll account for that extra factor of 10. So unfortunately, we're going to have to run this thing. Okay, run it all. Okay, good. So let's go here. Make this thing bigger. Let me delete this graph that I created. Do it again. Right click, 2D, generate 2D display. Say finish. Go and pick your. Let me minimize this. Go and pick the node that you wanted right there. I don't want the displacement X and Y. Just said add. Okay. And if you make this thing bigger, restore. Remember, we changed this thing to from amplitude to real. Okay, and we also changed our units options. I put the cursor on this white area, right click option, and options define and apply right here. 3059, 3059. Now, when you compare this thing with Abacus Run, they're pretty close. If you do the problem with a linear element, either in Abacus or in Catia, of course, these relatively are close to each other. Okay, but these are of course much better. So when you go with a poor element, few of them, then don't expect miracle. But at least when you go to parabolic, they're now. My plan is to do this same problem in Abacus, but I'm not going to put it as part of this series because this series of videos are for composites in Catia's native solver. But if you want to know how to run the same problem, model the same problem, and run it in Abacus so that you can match it against these results, I will prepare a video for that and I'll put it up there. Now, the other thing is that we're going to come back and repeat this problem, except that we're going to put a instead of let's say a motor on in the middle section, all right, so that this thing, the load is sinusoidal. It's not a constant, it's a sinusoidal, and I'll show how to do the problem. All right, good luck. There's more steps, as you can see, right there. Static, frequency, transient dynamics, in order to get things like this done. Good luck.